Welcome to the deep dive. Glad you could join us. You're probably here because you want to get right to the heart of complex topics, avoid getting swamped by information overload.
Exactly. And today, we're jumping into something really interesting, cooperative multi-agent learning. Basically, how do we get lots of AI agents, robots or software agents, to actually work together well?
Right. Think coordinating drones or maybe robots in a warehouse. It's all about getting them to act not just for themselves, but for the group goal.
Precisely. And the big hurdle is always coordination. There's sort of two main ways people tackle this.
Okay. What are those?
Well, you've got distributed learning, where each agent kind of figures things out on its own.
Okay.
And then there's centralized learning, where you have one main controller pulling the strings for everyone.
Centralized sounds powerful, having that overview.
Yeah.
But I guess there's a catch.
Oh, absolutely. Centralized methods can get really bogged down,
Yeah.
especially as you add more agents or they have more actions they can take.
Why is that?
It comes down to something called the joint action space. The central controller has to think about every single combination of actions all the agents could possibly take at the same time.
Ah, okay. So if you have like just a few agents,
Even then, the research we're looking at uses an example.
yeah.
6 agents, right? And each can do just 5 different things.
Okay, 6 agents, 5 actions each. Doesn't sound too bad initially.
You'd think, but the central controller has to consider 5 times 5, 6 times. That's 5 to the power of 6.
Which is,
15,625 possible combined actions at every single step.
wow, okay, yeah, I see the problem. That explodes really fast. That's the bottleneck.
That's the bottleneck, exactly. It's a well-known issue, and that's what makes this research so relevant,
So the mission for this deep dive then,
is to explore a pretty novel, centralized approach that tries to get around this exact problem. It uses this idea of a supervisor, meta agent.
a supervisor.
Yeah, and a clever trick called sequential abstraction. It basically avoids dealing with all those joint actions at once.
Okay, intriguing. So hopefully our listeners will get a good handle on how this simplifies that whole coordination mess.
That's the plan.
All right, let's dive into this supervisor idea. How does it actually dodge that joint action explosion?
Well, the core concept is pretty neat, actually. The supervisor doesn't try to pick one giant joint action from those thousands of options.
Okay, so what does it do instead?
It assigns actions to the agents sequentially, one after the other. Like it's going down a list, deciding for agent 1, then agent 2, then agent 3, and so on.
Huh, that sounds way simpler. So back to that 6 agent example, 15,625 joint actions normally. What does the supervisor deal with?
At each step of its sequence, the supervisor's choice is just like a single agent's choice. It only has 5 options: assign action 1, assign action 2, up to assign action 5.
Just 5 options instead of over 15,000.
Exactly. It's a massive reduction in the complexity of the decision the supervisor itself has to make at any given moment.
That's a huge difference. But wait, how does it know which of the 5 actions to assign to, say, agent 3 if it hasn't decided for agents 4, 5, and 6 yet? Doesn't it need the whole picture?
Ah, good question. That's where the concept of the metastate comes in. The supervisor isn't just looking at the environment, the outside world.
Okay.
The information it uses to decide includes the current state of the environment plus the list of actions it has already assigned to the agents earlier in the sequence.
Ah, I see. So it knows, okay, the environment looks like this,
Yeah.
and I've already told agent 1 to go left and agent 2 to wait.
Precisely. That combined information environment state plus the history of assignment so far, that's the metastate. It lets the supervisor tailor the action for the current agent based on what's already locked in.
Got it. So it's like building the team's plan piece by piece, informed by the pieces already laid down.
Exactly right. And only when the supervisor has gone through the whole sequence, assign an action to every single agent,
Then what happens?
then the complete joint action, the result of all those sequential assignments, is executed in the actual environment.
And the environment reacts, agents get rewards, and the whole process starts again for the next time step.
Yep. The paper has a figure, too, that apparently shows this flow pretty clearly, building up the joint action sequentially.
It's a really clever way to reframe the problem, taking this complex multi-agent thing and making it look like a single agent problem for this supervisor. How do they formalize this in reinforcement learning terms?
Yeah, they talk about compiling the original multi-agent problem, the MMDP, into a new abstract single-agent problem, a standard Markov decision process, or MDP, they call it M prime.
M prime. Okay, let's break that down. What are the states in this abstract M prime world?
So the states, S prime, are exactly these metastates we just talked about. It's a combination of the original environment state, S, and this sequence L, which tracks the actions assigned so far.
The sequence L.
Right, and if an agent hasn't been assigned an action yet in the current sequence, its spot in L is just marked with a placeholder, like a dash.
So the supervisor's worldview includes what is already decided internally.
Exactly. That list L is part of its state.
Okay. And the actions for the supervisor in M prime, A prime.
The actions A prime are these meta actions. Assign action A, where A is one of the things an individual agent could do.
So if agents can move north, south, east, west.
The supervisor's actions are assign north, assign south, assign east, assign west. Simple as that.
Right. Makes sense. Now, how does the supervisor learn which sequence of assignments is good? What's the reward, R prime?
Ah, that's quite critical. The supervisor gets 0 reward while it's in the middle of assigning actions. R prime is 0 for assigning to agent 1, agent 2, etc.
No immediate feedback.
Nope. Only when the entire sequence is complete, all agents have actions, and that final joint action gets executed in the real environment.
Then it gets a reward.
Then the supervisor receives the meta reward, R prime. And that reward is simply the sum of all the individual rewards the agents got from the environment because of that joint action.
Interesting. So it's only judged on the final team outcome? That really forces it to think about overall cooperation, doesn't it?
It does. It incentivizes finding sequences that lead to good collective results.
Okay, and the start. The initial state, S prime 0.
That's just the initial environment state at 0, paired with a sequence L that's all dashes no actions assigned yet.
Makes sense. And the transitions, T prime. How does the meta state change?
Right. There are basically 2 cases, which they lay out in their procedure 1, sort of pseudocode. Case 1. The supervisor assigns an action, but there are still more agents left in the sequence.
Okay.
In that case, the environment state S doesn't change yet, but the sequence L gets updated with the action just assigned, and the supervisor moves on to consider the next agent. It's just updating its internal plan.
Got it. And case 2.
Case 2 is when the supervisor assigns the action to the last agent in the sequence. Now the joint action is complete.
And that's when things happen in the environment.
Exactly. That complete joint action is executed in the original multi-agent environment. This might change the environment states and the agents get their rewards. Then the sequence L gets reset back to all dashes, ready for the supervisor to start building the next joint action.
Okay, I think I've got the flow now. Simplify the action choice, but manage the sequence. But doesn't this just push the problem somewhere else? Like, the number of actions is small, but the number of possible metastates must be huge, right? With all those combinations of environment states and partial action sequences.
That's a very sharp observation. And yes, you're absolutely right. The researchers are upfront about this. The metastate space, S prime, does become larger, potentially much larger.
So have we just traded one kind of complexity for another?
Sort of, but it's a strategic trade. And here's the key advantage they point out. Deep reinforcement learning, DRL, the kind of AI algorithms they use. DRL methods are actually remarkably good at handling very large, complex state spaces. They can find patterns, generalize. That's where they shine. But those same DRL methods often really struggle when faced with a massive number of possible actions at each step. That huge action space makes it hard to explore efficiently and learn a good policy.
I see. So the trade-off is make the state space bigger, which DRL is good at handling, in order to make the action space much, much smaller, which DRL finds difficult.
Exactly. It's about playing to the strengths of modern DRL. It's like saying the map might be more detailed now, bigger state space, but at every crossroads there are far fewer roads to choose from, smaller action space.
That's a clever strategy. Let the DRL focus its learning power on understanding the complex state patterns, rather than getting lost exploring zillions of actions.
Precisely. The hope is the DRL supervisor can learn the connections within that big metastate space to make smart sequential choices.
Okay, the theory sounds solid, but, the proof is in the pudding. How did this supervisor actually perform in practice? Did they test it?
Oh, yes, they did. They evaluated it quite thoroughly using 3 different multi-agent environments from a standard platform called MAGYM.
3 different ones. Why 3?
To get a range of different cooperative challenges, you see. They had different dynamics. First up was switch.
Switch, what's that?
It's a grid world. Agents have specific colored target tiles they need to reach, usually at opposite ends of a corridor or grid. The trick is they have to coordinate to pass each other without getting stuck or blocking the way.
Okay, sounds like a fundamental coordination test. What was next?
Second was traffic junction. Pretty much what it sounds like. A simulation of cars, autonomous vehicles trying to get through a four-way intersection.
Without crashing, I assume.
Without crashing.
Good.
Each car has a set route it needs to follow, so it really tests timing and avoiding collisions in tight spaces.
Right, that sounds like it requires more precise interaction. And the third environment?
The third was called combat. This is more strategic. You have a blue team of agents controlled by the learning algorithm, and they have to defeat a red team controlled by the environment's rules. So it's about teamwork, strategy, maybe some agents acting a bit more independently, but towards that common goal.
Wow, yeah, that's a diverse set. Grid coordination, traffic timing, team combat. Covers a lot of ground. How did they train the supervisor agent in these?
They used a well-known DRL algorithm, proximal policy optimization, PPO. It's an actor-critic method, pretty standard for this kind of thing.
Actor-critic.
Yeah, one part, the actor learns the policy what to do. The other part, the critic, learns to judge how good the states or actions are. Helps stabilize the learning.
Okay, and they just trained it in each environment.
Yep, ran multiple training sessions, tried different numbers of agents too. And they also tested giving the supervisor just the individual agent observations versus giving it a sort of global view of everything.
Oh, interesting. Did having that global view help?
Actually, surprisingly, no. Looking at their training results, Figure 4 in the paper, they found the training loss, basically how wrong the predictions were, generally went down nicely in switch and combat, meaning it was learning.
Good sign.
But traffic junction was more up and down, more variable, and crucially, giving the supervisor that collective global information didn't seem to improve things. Sometimes it even looked like it made training worse.
Really? More information made it worse. That's counterintuitive.
It is a bit, yeah. Maybe the sequential focus makes it better at using just local info. Anyway, because of that, they focused their final evaluations on the cases using only individual observations.
Okay, so training showed promise, especially in switch and combat. But traffic junction was a bit rockier, and global info wasn't the magic bullet. How did the fully trained supervisors perform in the end?
For the final evaluation, they ran the trained policies many times and looked at two main things: the absolute best reward achieved in any single run, and the average reward across all the runs.
Best versus average. Makes sense.
And they compared these scores to the known optimal reward you could possibly get in each task. Table 2 in the paper summarizes this.
Okay, moment of truth. What do they find?
This was probably the most striking result. For all three environments, switch, traffic junction, and even the complex combat scenario, the best reward achieved by their supervisor approach actually matched the theoretical maximum, the optimal reward.
Wait, it achieved perfect scores, even in combat.
In at least one run for each task, yes. The peak performance hit the ceiling. It suggests the framework can find optimal coordination strategies, even for quite difficult problems.
That's really impressive.
Yeah.
It shows the potential is there to completely solve these coordination tasks without hitting that scalability wall.
It's a strong piece of evidence for the approach, definitely.
It's always a but. What about the average rewards?
Right. The average results told a slightly different story. While the peak was optimal, the average reward in traffic junction was quite a bit lower than the optimal score.
So it could be perfect sometimes, but wasn't consistently perfect in the traffic scenario.
Exactly. Whereas in switch and combat, the average rewards, while maybe not always hitting the absolute maximum, were generally much closer to the optimal values, more consistently good performance there.
Okay. So switch and combat. Good peak, pretty good average. Traffic junction. Good peak, but lower average. Why the difference? Why might traffic junction be harder to get right consistently?
The researchers themselves speculate about this. They think it likely comes down to the nature of the interaction required.
How so?
Traffic junction seems to demand really precise, continuous, moment-to-moment coordination between all the cars at the intersection. One slightly wrong move or timing issue can cause a failure. There's very high interdependence.
Right. Very tight coupling between the agent's actions.
Yeah. Compare that to switch, coordination is needed, but maybe it's less about split-second timing and more about just not blocking paths. And combat. Well, it's complex, but perhaps individual blue agents can sometimes act a bit more independently flanking, targeting while still contributing to the overall team goal of defeating the red team.
So the supervisor approach, assigning actions one by one, might just be inherently better suited to tasks where agents don't need quite that level of constant, super tight, simultaneous adjustment.
That seems to be the hypothesis, yes. Where agents have a bit more leeway or the coordination is more about sequencing than perfect simultaneous timing, the approach seems more robust on average.
Interesting. So it nails the action space problem, can find optimal solutions, but its consistency might depend on how tightly coupled the agents need to be second by second.
That seems a fair summary of the findings. It's a powerful approach, but like any method, it probably has scenarios where it shines more than others.
Okay, so let's try and wrap this up. If we had to boil down the key takeaway from this deep dive into this supervisor framework for multi-agent learning,
Yeah.
what would it be?
I'd say the main message is that this sequential supervisor idea is a genuinely effective way to tackle that massive action space problem in centralized multi-agent control. It really does simplify things.
Making it feasible to apply powerful tools like deep reinforcement learning.
Exactly. And the fact that it could achieve optimal performance across different kinds of tasks, even complex ones, shows its potential. It's a significant step.
But, as we discussed, it's not necessarily a silver bullet for all coordination problems, especially those requiring extremely tight continuous interaction, like we saw with the traffic junction averages.
Right. The limitations are important too. The results suggest there's still work to be done, maybe exploring variations or hybrid approaches for those highly interactive scenarios. Future research will likely dig into that.
Fascinating work. It definitely gives you a new way to think about managing complexity.
It does.
And maybe for our listeners, a final thought to ponder. This whole idea of using a supervisor to break down a complex, simultaneous problem into a sequence of manageable steps, where else might that apply? Not just in AI, but maybe in managing complex projects or teamwork flows, or even, how we approach complicated decisions in our own lives. Could abstracting the complexity with a sequential approach be useful elsewhere?
That's a great question. Thinking about problems in terms of sequences rather than huge simultaneous choices, it's a powerful mental model.
Something to mull over. Well, thanks for sharing these insights today. It's been a really interesting exploration.
My pleasure. It's exciting stuff.
Indeed. Thanks, everyone, for tuning into this deep dive. We'll catch you on the next one.